spectroscopy. So Mossbauer spectroscopy, it's not as like every spectroscopy. There are some differences here. As usual, we know in a spectroscopy there will be a source. Then the source, it might be an electromagnetic radiation, and this will be ejected to the sample, and then it will be transmitted to a detector. So this is the working principle of a spectroscopy. So in case of Mossbauer spectroscopy, the source will be producing gamma radiations. As we know, gamma radiations have some significance. They are very high intensity radiations. Also, this gamma rays, when gamma rays are emitted, the source will be moving backwards. And when it is hit on a sample, the sample will be also moving, because it is this specialty of a gamma radiation. So Mossbauer spectroscopy is discovered by Rudolf Mossbauer in 1958, and this was a Nobel Prize winning breaking technique. And also this method is based on recoil free emission and absorption of gamma rays in solid crystalline materials. So this is a very important, or this is the very basic principle of Mossbauer spectroscopy. So here recoil free emission. So what is recoil? Recoil free emission is that when a gamma radiation is emitted from a source, the source will be moving backwards. And also when it is emitted to a sample, the sample will be also moving away from the source. There is a movement of the sample and the source. So during setting up a Mossbauer spectroscopic arrangement, we generally use a movable source. Okay, movable source. The source is moved so that it is adjusted for proper gamma ray radiation and for hitting the sample. Also, in Mossbauer spectroscopy, majorly we consider three important characteristics. That is, first of all, movable source. Also, the solid sample should be taken. That is why I said this line is very important. Solid sample should be taken. Also, this is conducted in a low temperature region. Also, by exploiting the hyperfine interaction, Mossbauer spectroscopy provides a powerful window into the nuclear and electronic environments of atoms within solids. Then, Mossbauer emission and recoil free emission. So we know normal gamma emission. When a free nucleus emits a gamma ray, conservation of momentum requires the nucleus to recoil, causing significant energy loss and shifting the gamma radiation. Also, lattice absorption. In a solid crystalline lattice, the entire crystalline structure absorbs the recoil momentum collectively. The mass is so large that recoil energy becomes negligible. Also, resonance achievement. With minimal recoil energy loss, gamma rays are emitted and absorbed at nearly identical energies. Also, exceptional resolutions. The phenomena enables energy resolutions in the order 10 raised to minus 11 electron volt, one of the highest in spectroscopy, allowing detection of minute nuclear energy changes. So this is basically the principle of Mossbauer effect and recoil emission, recoil free emission. So also Doppler effect is one of the significant effect in Mossbauer spectroscopy. Doppler effect is nothing but, as I said, a source. When the source is coming close to the radiation, the frequency will be increasing. Consider a car. Okay, consider a car, and you are standing at a fixed distance from the car. When the car approaches to you, the frequency will be increasing. You have a frequency detector machine. Suppose you have it in your hand, and so when the car is approaching towards you, what happens? Yes, frequency will be increasing. Also, when the car is moving away from you, the frequency is decreasing. This is what Doppler effect is. Doppler effect means when the source is closer, the frequency will be increasing. When the source is moving away, the frequency will be decreasing. So, therefore, gamma rays do not interact. There is a variation in frequency. So that is velocity modulation. Velocity modulation, the radioactive sources mechanically oscillated at controlled velocity to systematically shift the gamma energy gamma ray energy. Also, there is a energy shift equation. This equation is very important because many CSR net questions is based on this equation. Direct substitution. They will be giving every quantity. You just want to find the chemical shift. Sorry, in case of here, it's frequency shift. Okay, you want to find the frequency shift. So you should by heart this equation here. V is the velocity, source velocity, C is the speed of light, and EV is the gamma ray energy. So on substituting these three values, we will be getting the shift, okay, Doppler shift or frequency shift. Also, velocity scale plotting. Absorption intensity is plotted against the source velocity. Source velocity is generally taken along x-axis. Absorption intensity along y-axis. We will get the Mossbauer spectrum that reveals hyperfine structure. Now, isomeric shift. As we have seen chemical shift in NMR, similar to that isomeric shift. Isomeric shift also, the major important point you should remember here is this Mossbauer spectroscopy is limited to certain nucleus. So iron and tin are commonly showing this Mossbauer active nucleus rather than those many other like tellurium, tungsten, iridium, gold, europium, gadolinium, dysprosium, erbium, ytterbium, neptunium, such nuclei also show, but generally iron and lead is considered to be the prominent one. Also, the point is in a question, it is asked like giving a collection of nucleus and which among them are Mossbauer active. A question was there in 1 year for CSIR. So options were iridium, cobalt, iron and lead. So which is inactive there? Cobalt is the only inactive Mossbauer nuclei there. Other than cobalt, iron, lead and iridium are iodine is also Mossbauer active. Now, coming back to isomeric shift, similar to chemical shift, isomeric shift arises from the difference in electron density at the nucleus between. So, okay, just take out the note. I'll explain it simply. The point is that in case of iron, radius like delta R will be negative. While in case of tin, it will be positive. In case of iron, since in case of iron, this delta, like the radius is negative, what the point is here is electron density, S electron density is inversely proportional to chemical shift in case of iron. Iron is an exception case, okay? In case of iron, this S electron density will be inversely proportional to the chemical shift. So as S electron density increases, chemical shift will be decreasing. Many questions regarding this topic is asked, okay? But in case of tin and all or other any radioactive, Mossbauer active nuclei, as S electron density increases, chemical shift also increases. This is the one point you should note. The second point is that when it comes to P and D electron densities, as P and D electron densities increases, S electron density automatically reduces. For every nuclei, it's the same, okay? It's not just for iron or tin. It's for every nuclei as the density, electron density in P and D increases, S electron density decreases. Okay, these are the two concepts that you should keep in your mind. So according to that, we have given the values of typical values of iron 2 plus, iron 3 plus and iron 0, okay? Iron 0 is used as a reference here. And why this is happening? Because iron 2 plus exhibit more positive isomer shift compared to iron 3 plus, because additional D3 electrons, the Fe2 plus screens the nucleus. Screening effect is actually the reason behind this concept, okay? So that is what isomeric shift. The other point you should remember here is most common used reference standard is sodium nitroprusside. In case of iron, when the source or the complex is iron, the most common reference standard reference is sodium nitroprusside. Okay, the reason is difference in electrodensity around nucleus. Then chemical information, it gives the oxidation state of an atom, degree of covalency in bonding, electron density redistribution, chemical environment and coordination. Also, the shift moves the entire spectrum center position along the velocity axis, providing a fingerprint of electronic structure. Okay. The next point, very important point. I think this is the last very important point here to discuss. It's quadrupole shifting. In case of quadrupole shifting, basically we should discuss two important cases. In presence of magnetic field and in the absence of magnetic field. In the presence of magnetic field, the splitting is based on symmetry. Okay, the how many peaks it shows, it's based on symmetry. Symmetry is again classified into two: ligand symmetry and electronic symmetry. Ligand symmetry will be spherical and axial. Similarly, electronic is also spherical and axial. So how we determine whether a given molecule is spherical or axial, ligand or electronically, we have actually done a separate video, please refer that. So on the basis of that, if they are symmetrically if they are spherical, both ligand and electronic case, two case we should consider. In both those cases, if those are active, if the given compound is active, they will be having electric field gradient to be 0. For those compounds, electric field gradient will be 0, and for such compounds, they will show only one peak. The other compounds will show two peak if they are not symmetrical, or if they are not spherical in symmetry with corresponds to ligand and electronic. Both cases we should consider. So in both cases, if they are not spherical, then what, the electric field gradient will not be 0, so that they will be showing two peaks. Okay, and here nuclear quadrupole moment, nucleus with a spin greater than or equal to 1 possesses a quadrupole moment. Okay, reflecting non-spherical charge distribution. In case of non-spherical charge distribution, we will be having a electric field gradient which is not equal to 0, so that they will be having two peaks. Asymmetric electron distribution around nucleus creates a electric field gradient EFG, which interacts with the quadrupole moment. When this EFG is not equal to 0, what happens is nuclear energy raises, splits into substrates, producing characteristic double patterns in spectrum. Okay? Yes. The next point that we should discuss is hyperfine splitting. Okay, in case of hyperfine splitting, magnetic interactions and magnetic information. So internal or in external magnetic field interact with nuclear magnetic dipole moment, splitting the nuclear energy level. So as I said, during quadrupole splitting, we have two cases: in the absence and in the presence. In the presence, what it happens is, if in the absence it shows two peaks, in the presence it will be showing 6 peaks, because the both energy levels I 1 by 2 will be splitting into 2, plus half and minus half. I 3 by 2 will be splitting into 4. Which are they? Minus 3 by 2, minus 1 by 2, plus 1 by 2, plus 3 by 2. So, like that is what here it meant. In presence of magnetic field, the splitting is 2L plus 1. Okay. Then that is what I said, 6-set pattern. For iron, 3 by 2 is one case, and 1 by 2 is the second case. 3 by 2 will be splitting into 4. This 1 by 2 will be splitting into 2. So that producing 6 allowed transitions. Then hyperfine field strength and line intensities reveals this magnetic ordering, spin orientation, domain structure and electronic configuration. Now representative Mossbauer spectra. So in case we have 3 cases given. First of all, metallic iron. So it will be showing a single sharp 6-set center at 0 velocity. For iron oxide, the distinct isomer shift and quadrupole doublets differentiate Fe2 plus and Fe3 plus. Hematite shows a 6-set which shows doublet at room temperature. For magnetite, Fe3O4, what overlapping 6-set is arising from Fe3 plus in tetrahedral and mixed valence in octahedral. Okay, actually this is not as such important, just to make you aware this is how a Mossbauer spectra looks like, so that only I included that. Now coming to the applications. of Mossbauer spectroscopy in mineralogy and geology for determining the oxidation state of iron, coordination, environment, mineral phases. We'll be using the spectroscopy. Then coordination chemistry, most probably in probing metal ligand bonding, electron delocalization, spin states, and coordination geometries, geometry in organometallic and inorganic complexes. Then metallic materials, like characterizing metallic ordering, hyperfine fluids. Then in material science, like corrosion product, catalyst, nanoparticles, and all, we use this Mossbauer spectroscopy. Then in case of archaeology and art, for non-destructive analysis of pigments, corrosion layers, and provenance studies in cultural heritage objects and ancient artifacts. Then in biochemistry, we'll be using for investigating iron containing enzymes, proteins like hemoglobin, ferritin, and metalloproteins to understand their function and electronic structure. So in total, what we covered is Mossbauer spectroscopy, there which we discussed isomer shift, quadrupole splitting, magnetic splitting, and Doppler's effect. Doppler effect, okay? Yes. Hope it's clear. Thank you.